Taylor series, we have a Taylor's theorem. So what does it say? So we start with an f, and its n derivatives here. Let's consider them are all continuous on a closed interval between a and b, and f to the n is differentiable on the open interval between a and b. Then there exists a number c between a and b such that f of b is equal to f of a. So we have all these Taylor polynomials up to here, but we stop at c. The last term is going to be that. So Taylor's theorem says actually this last term is going to represent kind of the rest of the the rest of the Taylor series. Okay. We have a Taylor's formula as well. F has derivatives of all orders in the interval containing a. Then for each positive integer n and for each x in I, f of x can be written as f of a, f prime a, x minus a, f double prime a, 2 factorial x minus a squared, etc. You're going to go until n, and you're going to have a remainder, Rnx, okay? This remainder is actually the one that we got from the previous formula. This is going to be true for some c between a and x, okay? What is special about this remainder? This remainder actually, as n goes to infinity, this goes to a 0 for all x in the interval. If this Rnx goes to 0, then we say that Taylor series generated by f at x is equal to a converges to f itself on that interval. And we write f of x is equal to this. But we want to make sure that Rnx goes to 0 on an interval as n goes to infinity. There's a remainder estimation theorem. I'm going to skip that. We don't need that. Let me see applications of the Taylor series. Yeah. There are some applications, of course. Yeah, this is what I want you to see. Of course, if I could be writing them, it would be easier. Do you remember this 1 over 1 minus x is a graph I gave you, and then I said 1 plus x, 1 plus x plus x squared, blah, blah. They are going to approach, actually, they do. So this 1 over 1 plus 1 minus x can be written as this power series, or Taylor series. Okay, you can say. They are equal, but they are equal in this interval, not elsewhere. So the radius of convergence is 1. 1 over 1 plus x can be written like alternating Taylor series like that, and radius of convergence is 1. E to the x can be written like that, and radius of convergence is infinite. Okay, sine of x can be written like that, and radius of convergence is infinite. So in other words, the functions that we already know, we can write them as a series of functions. Okay, that's good. Series of functions like that, Taylor series. Cosine x can be written like this in this infinite radius of convergence. And then 1 plus x can be written like this in a half open interval like this. Arctangent can be written like this in closed and bounded interval with radius of convergence 1 here. That's what actually we want you to know. In your next class, probably you'll learn more about this.